Okay, now we're going to learn what's called, there's two Kirchhoff rules. And we're going to use these Kirchhoff rules later on when we analyze circuits. And if you're wondering why do you want to analyze a circuit, well, that's if you're a medical student, that's how they describe blood going through various veins and arteries and organs and all that. So the methods that we'll learn with circuits, they actually use in medical school. But anyway, Kirchhoff's rules. So this is a circuit diagram. So this is a battery. These are wires. And these are something called resistors. I'll get into it, don't worry, all right? So wires, resistors, and batteries. Now, you've got to be careful. Some books with the batteries, they have 4 horizontal lines. Some books, 2 horizontal lines. So, you know, just, I don't know. It's the same thing, so just be aware, right? And it's nice to label them so you see that the longer is a plus, the shorter is the minus. Right? Longer plus, shorter is minus. Okay. Okay, so these are called junctions for obvious reasons because they're junctions, right? That's where the wires intersect or meet. All right, so junctions. So, you know, here's current coming in and there's current going out. Let's just say there's current going out. So what's going to be true about the current, this current, this current, this current? You know, think about what we learned a few minutes ago. What's going to be true about those currents at a junction? Well, current is conserved, right? So therefore, all of the currents going in have to equal the sum of the currents going out. So that's the first Kirchhoff rule. It's called the junction rule. The sum of the currents coming in at a junction equals the sum of the currents going out of a junction. And again, it's nothing new, right? It's just conservation of current, which we already discussed. Okay, so those are junctions. Now we have loops. Now I didn't draw every loop, I just drew 4. So let's just talk about this one. All right? So what you're imagining is current going through or around this loop. Okay? Now, a loop, the important thing is the loop has the same starting and ending point. Okay? That's the important thing. So let's say we have I'll say electron, all right? Let's say we have an electron here with 0 energy. Then it goes through the battery, gets some energy, right? That's what a battery does. Then it goes on a loop, gives up its energy to this resistor, which could be a TV set or who knows what. Then it comes back here, it has 0 energy again, right? So what did you notice? It started out with 0 energy, 0 joules. Then it gave up then it got some energy. Let's say it got 9 volts. I mean, let's say it got 9 joules. Okay, let's say it's a coulomb of charge. So it has here 9 joules of energy, gives up the 9 joules of energy here, and then comes back to 0. So therefore, so I talked about energy. Well, same thing with volts, right? Let's say 0 volts, 9 volts, gives up the 9 volts here, comes back at 0. So what's the sum of the voltages around a loop? 0, right? 0. So that's a Kirchhoff voltage rule. The sum of the voltages around a loop, which means you start and end at the same point, is 0. Here's an example. So let's say we start at, I don't know, start here, start at point 1. So this is a 20-volt line. Right? Remember those equipotential lines we learned about earlier? This is a 30 equipotential line. This is the 40-volt equipotential line. So we start here at point 1. So we have 20 volts, right? Because everywhere along this equipotential line we have 20 volts. So we go from here to here, so here to here. What happens? Nothing, right? Because we had 20 here, 20 volts, 20 volts. Then we go up here from 20, so we've gained, go from 20 to 30, so we've gained 10. Here to here, nothing. Here to here, we've gained another 10 volts, right? Because we go from 30 volts to 40 volts. Then we go here, nothing, no change, right? Because we're on that equipotential line. Then we go from 40, zip, back to 20. So what have we done? We gained 20 here, we lost 20 here. So what's the net? The sum of the voltages is 0, right? We started off with 20, we ended up with 20. So the sum of the voltages around this loop is 0. So that's what we mean by that. So we'll use that a lot later on. Okay, now here's kind of a picky little thing, which I'm just going to explain it now and we'll use it later. I'm sorry, that's kind of how this chapter is. Okay, there's something called an EMF. EMF. And that's what we call it. We don't say anything else. It's not an acronym, just an EMF. Okay? And we denote it by this script E. That's a script E. You don't want to write it like this, because that's an E field, right? And it's completely different, right? So if you want to talk about EMF, it's always this funny-looking script E. So what's an EMF? So a device, like a battery, has an EMF. And what it is, it's the work done by the chemicals or whatever in the battery to separate the charge divided by the charge, but divided by a charge, okay? So it's the work per charge. That's better, right? Work per charge that's done by the chemicals or whatever in the battery to separate charge, okay? Now, for an ideal battery, what's an ideal battery? An ideal battery is a battery with no resistance, okay? Right now, we're just learning about ideal batteries. Later on, we'll talk about real batteries. Real batteries have a really, really small amount of resistance. But for ideal batteries, the EMF is just equal to voltage, right? All right, so that's the thing. For ideal battery, the EMF is just equal to delta V battery. But so why are you saying, well, why, if it's the same thing, why even talk about it? Well, when you talk about voltage, you're talking about electricity, right? Electricity, electrical forces. When you're talking about EMF, it could be chemical forces or who knows what, right? So, I mean, yeah, I know they're related, but they're different. Electricity, chemical, but they're both work over charge, okay? That's really all there is to it. Now, look at this. You've seen this before, I know, but so here's a battery with a wire. So look at delta V battery. This is low potential. This is high potential. Since we have positive charge carriers in our conventional current, what do? They go from high potential to low potential. Well, where have you seen that before? High gravitational potential to low gravitational potential. So that's what I mean. That's what's nice about talking about conventional current with positive charge carriers. It just follows along with, gravity. So we like it, all right? We like it, all right? Okay, so we could say that the positive charge carriers go from high potential to low potential. We could also say F equals QE, and it has to be a force, an electrical force in the wire to push those positive charge carriers. You can look at it either way you want. I think it's somewhat easier to talk about just going from high potential to low potential. So we'll do that most of the time. Okay, so let's read it. So the electric field drives a conventional current through the wire. The current is in the direction of decreasing potential. No kidding, right? Positive charge carriers want to get away from this and towards this, okay? Or you can think of it high potential to low potential. Okay, here's a question for you. A battery is a source of what? And there's more than one correct answer. So pause your video and get ready to vote. Okay, so what is a battery a source of? Well, it's certainly not electrons. The electrons already are in the wire. And certainly not the positive charge carriers because, well, first of all, they don't even exist. But second of all, assuming they do exist, they're already in a wire as well. So what's a battery a source of? Well, all three, the last three, right? Electrical potential energy, the battery gives those charge carriers energy, just like lifting weights. Gives the barbell potential energy. It's a source of voltage, because voltage is related to potential energy. And you can say it's a source of EMF, right? EMF. So there you go. All right, now we're going to learn the most important equation in all of electricity. It's called Ohm's law. It's kind of funny because it's not really a law, but we don't care about that. All right, so here we have a real wire. Okay, a real wire. So in other words, when we talked about wires in the past, like when I drew my circuit diagram, we assumed that there was no resistance, that the charge carriers just sped right through those wires. No resistance whatsoever. But now we want to talk about reality. So here's a wire. Let's say it has cross-sectional area A. We're going to assume it's a circle. Has length length L. So there's going to be a potential difference, delta V. And there's something called resistivity. So resistivity is a property of a material. All right? If something has high resistivity, it's really hard for the charge carriers let's be real. It's really hard for the electrons to plow through. If it has a small resistivity, it's easy for the electrons to plow through. Right? So this depends on the material. Okay? And here's the conventional current I. Right? So this is Ohm's law. So the potential difference of the voltage drop, delta V, equals the current times the resistivity times the length divided by the cross-sectional area. Okay? So, but, all right. We're going to make it simpler. Okay, don't worry. We're going to make it simpler. So let's just look at this thing. Okay? So think about it. Let's just say you have a copper wire. So it has a certain resistivity, right? That just depends on the material, right? So we can't change that. But now let's say that we make L like super, super long. Well, is that going to make it easier or more difficult for the electrons to plow through? Well, it's going to make it more difficult, right? I mean, what's easier, getting water through a hose this long or a hose a mile long, you know? Okay, so if we have a really, really long L, it's going to be harder and harder to get those electrons through it. On the other hand, what if we have a really big A? Is it going to make it easier or harder for the electrons to plow through? Well, easier, right? Easier, okay? All right, so this is what we're stuck with. This, by the way, this is not a P, it's a rho. Sometimes we use rho for density. When we did fluids, we use it for density. So it's not a P, because P is momentum. It's rho, Greek, you know, curves there, right? That's the resistivity. Okay, so all right, so we're stuck with this. If we make that big, it's going to be harder for them to plow through, the electrons to plow through. If we make this big, it's going to be easier, right? So this is called the resistance. It's the resistance of the wire. So uppercase R is the resistance, okay? So if this is big, that's going to be big. If this is big, that's going to be small. That's why, you know, that's on the top, that's on the bottom, right? So that's the resistance of a wire, rho L over A. You're going to play around with this in lab. All right. So it's the wire's resistance to the flow of electrons. Now let's look at the units. So we have resistance, rho L over A. So the unit is ohms. It's ohm. It's an uppercase Greek sigma. All right, ohm. All right. Now let's play around. So the units of resistivity are ohm meter. Length is meter. Area is meter squared, right? And so that, so the resistance is ohms. Okay? So I mean, for a given wire, you know, this depends on the material. If it's just a given wire, this is constant, that's constant. So for a given wire, this is always just constant, right? Just a constant, you know. You just calculate it or measure it. So this is how you should remember Ohm's law. Delta V equals IR. That's kind of like the F equals MA for electricity. If you talk to any electrician, you say, what's Ohm's law? They'll say delta V equals IR. I mean, everybody knows it, right? So delta V equals IR is Ohm's law. But remember, R is rho L over A, and that's constant for a given wire. All right? Okay, now, why do I put quotes around the law? Well, because it's not a law, all right? It only works for conductors. It doesn't work for other things. Oh, by the way, yeah, here are some resistivities. And look at the units, ohm meter, right? Ohm meter. Okay, so, you know, these are conductors, so you expect them to have a really low resistivity, right? And look at, you know, 1.47 times 10 to minus 8. I mean, these are all times 10 to minus 8 because they have low resistance. No kidding. It makes sense, right? Then you look at an insulator. Look, 5 times 10 to the 14th. I mean, super large. Well, that makes sense. Okay, let's look at the human body. Okay, look at air, 10 to the 20th. It's very large, right? Now, I suppose that's probably dry air. Lung, 1,400. Blood, 150. Yeah, you know, not so. Anyway, heart muscle, liver, kidney, bones, and da-da-da-da. All right? So there are some values of resistivity. Now, like I said, this only works for conductors. Wires doesn't work for other things, so we got to be careful. So let's look at this graph. Okay, so start with V equals IR. Now, for whatever goofy reason, whoever did this, by the way, sometimes you write V equals IR, you're just lazy. What you really mean is delta V, right? Because there's a potential difference between each one end of the wire and the other end. Okay, so for whatever reason, whoever made this graph decided to plot I versus delta V. Oh, whatever. Do whatever makes you happy, right? So let's solve for I. Because remember, we want it Y equals mx plus b, right? The equation of a straight line. So let's solve for I. So I equals 1 over r times delta v, right? That's good math, okay? So if you're going to plot I versus delta v, it's going to be, remember, r is a constant, right? So it's going to be a straight line, a straight line. But what's the slope? The slope is 1 over r, right? So slope is 1 over r. Okay? And I think I'll do something like that in lab. Okay. Now, so you look. Ohm's law says that the resistance is constant, so you're going to get a straight line, right? But, so this is in a situation where it works. So we call it an ohmic material. But let's say we have something that's not a conductor. Therefore, Ohm's law doesn't work. So look at it. I mean, here's a non-ohmic material, a diode. I mean, is that a straight line? Good golly, not. I mean, certainly not. So that means that the resistance is not constant. So Ohm's law does not work. So that's why, I mean, everybody calls it Ohm's law, but it's not a law, right? It only works for conductors, okay? Okay, now let's talk about something called superconductivity. This is kind of cool. Superconductivity. I got to write down some dates just so you appreciate this. I'll never ask a date on a test. Don't worry about it. But I just want to do it now. Okay, so 1911. So 1911, there was a guy, Onnes, in Denmark, that made this incredible discovery. He discovered that for mercury, the resistivity rho is exactly equal to 0. But there's a problem. So he discovered that for mercury, the resistivity is 0 when the temperature is less than 4.2 Kelvin. Now, kelvins. Now, if you had chemistry, you realize this is incredibly cold, right? So 4.2 kelvins is minus 452 Fahrenheit, which is equivalent to minus 269 C. Okay, so it's incredibly cold, all right? But still, it's amazing, right? So that means if you have a piece of wire that's made out of mercury and you get it this cold, since the resistivity is 0, the resistance is going to be 0, right? So that's called superconductivity because it's superconductive, right? Superconductivity means that the resistance is 0. Now later on, they found the same effect with some other materials. But again, it had to be at super, super cold temperatures. Now here's what's kind of interesting about it. There's no way in classical physics you can explain this. It requires quantum physics, which we'll learn. Well, we'll learn a little bit of quantum physics later on. All right, now look. It would be incredibly wonderful if we had superconducting wires. I mean, think about it. Let's say you have a power plant, 50 miles away, and they have to transmit electricity to the town, right, 50 miles. Well, they use real wires, and so there's resistance, right? So they lose energy, or you can say they lose power, or if you're an accountant type, you can say they lose money, right? They lose money to transmit the electricity. If they had superconducting wires, no power losses, no energy losses, no money losses. So you think, well, why don't they do it? Well, again, right here. Right? it's incredibly difficult and costly to keep a material this cold. It takes a very complicated, expensive cryogenic system. You know, they use lots of times they use liquid helium. I mean, liquid helium is not cheap, you know, to get something that cold, all right? So basically, since 1911, people have been trying to figure out, how can I get a material to become superconducting at room temperature? I mean, that would revolutionize the world, you know? So that's kind of like the big goal here. Try to figure out room temperature superconductivity. So let me show you the progress. Now remember, discovered in 1911. Okay, it wasn't until 1962 that people figured out how to make a superconducting wire. So that's when the first commercially made superconducting wire. 1962. That's 51 years after superconductivity was discovered. My gosh, right? And look at this. I mean, what in the world is niobium titanium, you know? Something you have at Sears and Roebuck? I don't think so. Okay. So this is really the particle physics community, because they wanted to make really, really powerful magnets. And you're going to learn later on that you make magnets by winding wire around like a conductor or a bolt or something like that, all right? Okay, so then the mid to late 60s, the first superconducting magnets were made in the UK. So it's great, but still, you know, you had to get them to liquid helium temperatures. 1970s, first superconducting magnets used in the United States. All right. 1986, breakthrough. Okay, so the critical temperature, that means that's the temperature that's required to get this thing to go superconducting, all right? So 1986, the critical temperature, 30 Kelvin. So it's the first time it's above liquid helium temperature. Whoa, people are excited. The problem is that the material was brittle and ceramic, you know, and it was normally an insulator. So how in the world are you going to make a wire out of that? You know, good luck, right? Again, people are trying to get room temperature superconductivity. So this is still really cold, you know? I mean, yeah, look at there. 32F, which is 0C, is 273 K. So this is really small. But it's above liquid helium, so they're making progress. 1987, breakthrough. Critical temperature 92 K, first time above liquid nitrogen. So they're getting there, right? They're getting there. Well, sorry. 2019, the world record, it still holds. 250 K. What in the world is this? Lanthanum hydride. But look at this. It only worked under a pressure of 170 gigapascals. That's kind of insane, right? And what's 250K? 250K is minus 23C, which is minus 9.4 F. So we're still far away from room temperature superconductivity, you know? But there's progress. But here's kind of something that's sort of sad. 2 decades of intense, it's probably 3 decades, of intense experimental and theoretical research with over 100,000 published papers on the subject have discovered many common features in the properties of high temperature superconductors. But as of 2020, there is no widely accepted theory to explain their properties. So that's the problem, right? So if we don't have a theory to explain high temperature superconductivity, how in the world can we develop it? It's just like, I mean, people are just, you know, it's like looking for a needle in a haystack. So that's basically what's going on in the world today. We don't have any theory to lead us along. And so that's why we're not making a whole lot of progress. Okay, now why do we care about this? I already explained it, right? When you transmit power over wires, you lose energy, so you lose money. The particle physics community was super excited about this because they wanted to make stronger and stronger magnets so they could accelerate their particles around, you know, particle accelerators and make them go faster and faster and faster. Superconductivity is used in MRI. You go to a hospital, get an MRI, they're going to have a superconducting magnets there. Today, I mean, in today's world, right, they use superconducting magnets in MRI. The magnetic levitational trains use superconducting magnets, so forth and so on. There is a theory that explains superconductivity at low temperatures, but unfortunately that theory does not work for high temperature superconductivity. So, if you want to become fabulously wealthy, super famous, win a Nobel Prize, for sure change the world, all you have to do is figure out room temperature superconductivity. Then you'll have more fame, glory, money than you know what to do with. So stay tuned. Okay, we want to end up with talking about power. And we've talked about power before. So power is just the change in energy over the change in time. And again, so here power is the change in energy over the change in time. So what are the units? So energy is in joules, time is in seconds. So a joule per second is a watt. You should know that already. Okay, so here's an electrical circuit. So what we want to know is we want to know how quickly does this battery, or power supply, how quickly does this supply energy to the circuit, okay? Or you can say, how quickly does the battery supply energy to in reality, right, to the electrons? Or in our fake world, how quickly does the battery supply energy to the positive charge carriers? And that's what it is, right? That's power, right? How quickly energy is delivered. Okay, so let's see. So let's just use definition. So we're talking about the power of the battery. I think I called it on the next slide, I call it power of the EMF. Same thing, right? So again, power is the change in potential energy over the change in time. By using an equation we had a while ago when you learned about potential, that's equal to the EMF. This is for ideal battery. So the EMF equals the voltage times delta Q divided by delta T, all right? So ideal wires, ideal battery, so see that? Okay. Now, what's delta Q over delta T? It's I. So it's just E, I, right? The script E is EMF, don't forget. Script E is EMF. Okay, so that's the equation. So that's the power of the battery, how quickly the energy is supplied to the circuit. It's the EMF, which is the voltage, times the current. Now, who cares, you say? Well, you go around campus, in the science areas anyway, you see these things all over the place. So these are called uninterruptible power supplies. You know how the power is sort of flaky in Hawaii? Sometimes you have power just turns off for a minute, or sometimes you get these power surges. Well, if you have sensitive electronics, like if you're doing an experiment, and the power goes flaky all of a sudden, you can destroy your experiment. Or if you're working on you're working on a computer or something like that, and the power goes off, you could lose your document. So all over campus, especially in the science area, people have these things, and they plug their computers in here. And so they have a battery, so if the power dies, you have like 20 minutes or something like that. But there's also surge protectors in this. So this is what the front looks like. This is what the back looks like. So you plug in all your computers and experimental stuff, whatever you want. But notice here, so this is the rating. It says 1500 volt amp. Volt amp. So if you only have like two computers, you can get you don't have to get a robust one of these things. You can get just a cheap one, right? If you have a whole bunch of computers and a whole bunch of equipment, where there's a lot of volts and a lot of current, you're going to get a more expensive model. So like if you go to the website for these things and you got to figure out which model you want to buy, they basically ask you, what are the voltages and the currents of the equipment that you're going to plug in? And then you figure out what kind of thing you want to buy. So there it is, okay? All right, now, so let's go back. Oh, you didn't see that? So this is the power supplied by the battery or the power supply to the circuit. And again, it's energy, right? It's how quickly energy is supplied to the circuit. Well, where's the energy go? I mean, what uses up? What dissipates the energy? How is the energy used up? Well, it's used up in the resistors, right? And again, what's a resistor? I mean, a resistor just stands for something that uses energy, right? That, like a light bulb or a refrigerator or whatever you want, okay? So this is what supplies the energy, and this is what uses up the energy, okay? So we have an equation for the power supplied. we also like to get some equation for the power dissipated, okay? So, and all we care about is magnitude, right? We don't care about the sign. So I'm just going to say power resistor. Well, again, energy over time, no kidding. And like we learned before, energy is charge times voltage. So we have delta V resistor, right? Then we have delta Q over delta, right? So that's your delta U. Then we divide by delta T. If I felt like it, I could write it like this. Oops, that's a Q. And what's delta Q over delta T? It's I. So we have I times delta VR. Okay? All right, so that's one equation. But, you never know how they're going to word the question, right? Or if in the real world, you never know what you're going to be able to measure and what you're not going to be able to measure. So we also know Ohm's law, right? Delta V equals IR, right? So if we felt like it, we could just substitute. We could substitute for delta V, right? We could say delta V is IR. So then we have I times IR, and that's I squared R. So there's another equation we can use. Or, let's solve for I. So I is delta V over R. So if we felt like it, we could look at this again. We can substitute for I, and we have delta V over R times delta V, right? And we get delta V R squared over R. Whatever, you can just play around with Ohm's law, and you can just change the equation however you want. So all I'm saying is that, so this is like the basic equation. The power dissipated by the resistor is delta V of the resistor times I. But then you can just use Ohm's law, and you can just change the equation. So why would you want to do that? Well, if the homework problem or the test problem, if they give you delta V and they give you R, they don't give you I. All right. If you don't know I, you're not going to use that. You're not going to use that. You're going to use that, right? On the other hand, if they give you I and R, but they don't give you delta V, you're not going to use that. You're not going to use that. You're going to use this. So, you have three equations. Just use the one that makes life easier. That's all. Okay, now, so what I'm saying is, here, this supplies the energy, this uses up the energy. So for ideal wires, right, ideal wires where we're not losing any energy in the wires, the power supplied has to be the power dissipated. So the power of the battery equals the power of the resistor. So i.e. battery equals all this stuff for the resistors. That's really all there is to it. Now, the energy is being used up by these resistors, right? And let's say we have a real electrical circuit with real, little resistors, okay? The resistors are using up the energy. So what's going to physically happen to the resistors? What do you think? They're dissipating electrical energy. They're using it up. They're going to get warmer, okay? And in fact, when you buy a resistor, they all have ratings, right? They have power ratings. Basically, if you exceed the power rating, the thing's going to burn up, okay? And so that's why, when you're trying to miniaturize things, heat is a real problem because, they can only dissipate so much power without burning up. So let's see, last fall in lab, we had a student who didn't follow the directions. And where's my picture? Hold on, there it is. We had a student that didn't follow the directions. And so the student exceeded the power rating of the resistor. So guess what happened? See all that brown? Here's a close-up, but it's not in focus. It's really bad. What happened to the resistor? It got burned up. All right? So that's just to show you that resistors have power ratings. Okay, so you got to be careful. That's all I'm trying to say. All right, so that's the chapter. Let's review. So we talked about and used conceptual model of simple direct current circuits, that battery or power supply, DC direct current. It just goes one direction. wait a minute. That's wrong. Get out of here. This is the wrong slide. That's a future chapter. This is us. Okay, we understand how charge moves through a conductor. Goes from high potential to low potential, you know. Or it goes if it's an electrons, it goes opposite to the direction of the E field. If it's positive charge carriers, it goes parallel to the direction of E field. We talked about a basic model for current, including conservation of current. We talked about how battery works. We talked about resistance, resistivity, and energy transfers. That's power. So you know, you've seen this before, right? With these electricity chapters, there's just equations, right? So the definition of conventional current, I equals delta Q over delta T in the direction of E, which means positive charge carriers. By the way, notice I don't say protons, because that would just be a lie. I say positive charge carriers. That's not a lie, because it doesn't exist. Tell that to your bishop in a temple recommend interview. Okay, junction. The sum of the currents in equals the sum of the currents out. Current is conserved. The loop rule. You go around the loop, the sum of the voltages is 0. You gain and you lose, or you lose and you gain. Ohm's law, delta V equals IR, right? The resistance, the resistivity times the length over the cross-sectional area is constant for a given wire. Power, you already knew this. Change in energy over change in time. Power supplied by a battery is the EMF, which is the voltage for an ideal battery, times the current. Power used up by, you know, the resistors, and again that stands for whatever, like light bulb or whatnot, is I times delta V. By the way, look, volts times amps. Volts times amps, right? It has to have same units, you know. And so this is it, I delta V, and you can use Ohm's law to get I squared R. You can use Ohm's law again to get delta V squared over R. So that is the chapter. Make sure you understand it really well, because we're going to apply it soon. Thank you.